Welcome to This Explainer. Today, we're tearing down the invisible architecture that keeps modern aviation-grade UAVs in the sky. We're going to break down the highly rigorous, multi-layered engineering, focusing specifically on aircraft design optimization and advanced system integration.
Now, you might be wondering, how does a drone actually achieve the safety of a massive commercial jet? Because let's be real, these aren't just glorified flying batteries anymore. They are highly complex, integrated systems operating in our airspaces and right over populations. Failure simply isn't an option here. They are bound by the exact same zero-tolerance safety expectations as a Boeing or an Airbus.
All right, here's our structural roadmap for today. 1. Certification and standards. 2. Structural design and MDO. 3. Engine units and FADEC. 4. ESC and battery management. 5. Smart energy management. And finally, 6. Power systems software design. Let's get right into it.
Okay, starting with part 1, certification and aviation standards.
Take a look at this. Under DO 178C, Design Assurance Levels, or DAL for short, we see safety classifications ranging from A all the way down to E. Now, a catastrophic DAL A failure literally means the aircraft would crash or cause fatalities. So, naturally, it requires the absolute strictest compliance. You see, in aviation, safety isn't just tested at the very end. It has to be mathematically proven throughout the entire engineering lifecycle. To actually clear that incredibly high bar, manufacturers have to jump through some major hoops. They need type certification, plus organizational approvals like APDO, DOA, and POA, alongside those ESA SORA SAI levels. They have to prove their design and production consistency can handle single or even dual-point failures. On top of all that, components go through RTCA D160G testing. Basically, engineers torture these parts with extreme temperature swings, brutal vibrations, and direct electromagnetic interference just to prove they can survive.
Moving right along to Section 2, structural design and MDO.
2.5 Gs. Under ASTM F2416 standards, that is the ultimate load test that critical structural joints have to survive. Engineering teams literally do a 1-to-1 scale physical static load test, pushing the entire airframe to 1.5 times its expected maximum failure load. Why? To absolutely guarantee it will never fracture mid-flight, even during violent maneuvers or massive wind gusts.
But here's the catch. You're always balancing weight and strength. It's the classic size, weight, and power dilemma. The modern solution to this is the MDO framework, or multi-disciplinary design optimization. Instead of the old traditional linear process where one team designs a wing and just tosses it over to the next department, MDO simultaneously calculates aerodynamics, structural stress, and thermal management all at once. It finds the absolute perfect integrated compromise in a single computational space.
And check this out. This optimization process includes low Reynolds number aerodynamics. It's actually a brilliant trick. By using genetic algorithms to subtly tweak the nonlinear twist of the airfoil, engineers can effectively stop the wingtips from stalling out early during low-speed cruise. So you maximize the lift-to-drag ratio without having to add heavier, reinforced wing structures. Up next, Section 3, Engine Units and FADEC. So propulsion comes in a few different flavors. You have electric setups like BLDC and PMSM motors, and then you have heavy fuel or aviation gas engines. Those combustion engines rely heavily on FADEC, Full Authority Digital Engine Control. Think of FADEC as a highly specialized digital brain specifically for the engine, replacing traditional mechanical carburetors to give you microsecond-level precision for fuel injection. Mechanical carbs simply cannot adapt fast enough to the rapid temperature and pressure changes a drone goes through, which is why ASTM E70 maintenance standards are so strictly enforced here.
But the real genius of FADEC lies in its resilience. Let's say the engine overheats. Instead of a catastrophic shutdown where the drone just drops out of the sky, the system intelligently uses power derating and fuel cooling to keep the drone limping along for a safe return. It uses closed-loop control with wideband lambda sensors, plus dual potentiometer verification for the electronic throttle, meaning if one sensor completely fails, the engine seamlessly switches to the backup to prevent a fatal plunge.
Which brings us to Section 4, ESC and battery management. Now let's look at the electronic speed controller, or ESC. It uses FOC's sinusoidal control over DR bus and drone CAN protocols. What does that actually mean? It guarantees that critical thrust commands are executed in under 2 milliseconds. And to prevent the system from burning out during heavy wind gusts, engineers build in a 30 to 50% current redundancy. There is always reserve power waiting when the flight controller demands a sudden shift.
On the power source side, strict safety standards like UL 2272 ensure that the battery system can survive severe impacts without going into thermal runaway. The Battery Management System, the BMS, acts as the absolute gatekeeper here. It's actively monitoring individual cell voltages and temperatures to prevent internal short circuits, even under the intense stress of a rough landing.
Moving on to Section 5, Smart Energy Management. Managing complex hybrid power, like combining a combustion engine with an electric battery array, is incredibly difficult. To handle this, AI dynamically allocates energy through a fascinating three-step process: reinforcement learning training, model predictive control allocation, and finally, Hamiltonian and simulated annealing optimization. The system is constantly predicting the drone's energy needs, calculating seconds into the future.
I really love this concept. The system dynamically shifts between mechanical and electrical energy to maximize flight time while minimizing heat. If the drone suddenly needs to dodge something, it dispatches the generator as a motor for a quick boost mode. But during a steady, efficient cruise, it cleverly siphons off that excess mechanical energy to recharge the onboard batteries. It is literally an elegant ballet of physics and code.
And finally, Section 6, Power Systems Software Design. The entire flight control platform runs on a strict real-time operating system, like NUTX. They combine DO-178C software guidelines with DO-254 hardware constraints. They even use anti-out-of-step communication designs to make sure the protocols never desynchronize. In this environment, every single millisecond is accounted for with hard, real-time precision.
And as you can imagine, rigorous static code analysis and independent verification are completely mandatory. Coding standards like MISRA-C strictly forbid dynamic memory allocation. Why? Because you absolutely cannot have a drone's computer run out of memory mid-flight. Every single piece of memory must be perfectly, statically defined before the aircraft ever leaves the ground.
100%. For DAL A-level software, developers are required to achieve 100% modified condition/decision coverage. That means every single logic branch is exhaustively tested. Every Boolean condition, every if-then statement, proven independently. The amount of documentation and testing required is astronomical, but it's the only way to ensure the code will never behave unpredictably.
So we've seen how integrating robust physical structures, smart energy allocation, and mathematically certified code creates a truly resilient machine. When you combine MDO frameworks, extreme environmental testing, and 100% code coverage, you don't just have a drone, you have a true aviation-grade asset.
But let me leave you with this final thought to ponder. As our drones become increasingly autonomous, and as deep learning algorithms take over more and more of those complex in-flight decisions, how do the rules of the sky adapt? I mean, can we statically test a neural network the same way we test a rigid line of C code? It's a massive question. Anyway, thank you so much for joining me for this explainer. I really hope this deep dive gave you a whole new appreciation for the intense engineering overhead flying quietly right above our heads. Until next time, stay curious.